There's a faint smudge of light in the night sky that most of us have never noticed. Hidden within it are nearly 1 trillion suns, and the light reaching your eyes tonight has been traveling for 2.5 million years. Tonight, we're going to explore a question that sounds simple, but opens into something vast. How big is the Andromeda Galaxy? Really, where are you right now? Lying in a dark room, or perhaps by a window with the night beyond? If this calm finds you, and you enjoy drifting into sleep, with science by your side, you're welcome to stay. Maybe follow along, leave a quiet like, or subscribe. So let your shoulders drop, take a slow breath, and let's begin. Tonight, as you settle into wherever you are, there is light falling toward Earth, not from the sun, which has long since dipped below the horizon, not from the moon, which may or may not be visible through your window. This light comes from somewhere else, entirely from a neighbor in the cosmos that has been shining quietly in the same patch of sky for as long as humans have looked upward. It comes from Andromeda, the galaxy nearest to our own. And though you might never have noticed it, that faint smudge holds secrets about the true scale of the universe. If you've ever stood outside on a clear night, away from the wash of city lights, you may have seen it without knowing what it was. A small, soft blur among the sharper points of stars. It doesn't demand attention the way bright stars do. It doesn't sparkle or pulse. Instead, it sits almost shyly in the constellation that bears its name, as if waiting for those who pause long enough to notice. And noticing it requires a kind of patience, a willingness to let your eyes adjust, to soften your gaze, to look not directly at it, but slightly to the side. To find Andromeda, you begin with Pegasus, the great square that hangs in the autumn sky. From there, you trace a line of stars eastward, following the figure of the Princess Andromeda from Greek myth, the one who was chained to a rock and rescued by Perseus. Just off to one side of that constellation, if the night is dark enough and your eyes are patient enough, you'll see it. Not a star, not a planet, something softer, more diffuse, like a thumbprint pressed gently onto glass. This technique of looking slightly away, of using the edges of your vision rather than the center, is called averted vision. It's a trick that ancient stargazers knew long before the science of optics could explain why it works. The rods in your eyes, the cells responsible for detecting faint light, are more concentrated toward the periphery. By looking just beside an object, you allow those sensitive cells to gather what the center of your vision cannot. It's a small act of trust, a letting go of the instinct to stare directly, and it reveals what would otherwise remain hidden. What's remarkable is that this modest smudge, this faint oval that seems so small and unassuming, is actually immense beyond comprehension. If your eyes were sensitive enough to gather all the light that Andromeda emits, it would appear more than 6 times larger than the full moon. It would stretch across a significant portion of the sky, its spiral arms arcing outward, its structure laid bare in all its complexity. But our eyes are limited. They catch only the brightest core, the dense heart of the galaxy, where stars are packed closely together. The rest fades into invisibility, hidden not by distance alone, but by the threshold of human perception. And yet, even in its dimness, even as a mere smudge, Andromeda is extraordinary. Because when you find it, when you finally see that pale glow hanging in the dark, you're looking at the combined light of nearly 1 trillion suns. Each one of those suns is a star in its own right, many of them larger than our own sun, many of them surrounded by planets. Some of those planets may have moons. Some may have atmospheres, weather seasons. Some may be barren rocks. Others may harbor conditions we can barely imagine. Each star, each planet, each moon is a world unto itself, and all of them are gathered together into a single structure, so vast that the human mind can scarcely hold it. The light you see tonight left Andromeda 2.5 million years ago. Think about that for a moment. 2.5 million years. When those photons began their journey, the Earth was a very different place. Our earliest ancestors were still learning to shape stone into tools. There was no language as we know it, no fire, no art, no cities, no agriculture. The light traveled across the emptiness of space, crossing the gulf between galaxies, while on Earth, species evolved climates, shifted ice ages, came and went, and eventually, after an unimaginable span of time, creatures arose who could look up and wonder what that faint smudge might be. So, when you see Andromeda, you are not seeing it as it is tonight. You are seeing it as it was frozen in a moment from deep prehistory. You are looking backward through time, witnessing a galaxy that has continued to evolve, to change, to birth new stars and lose old ones, all while its ancient light makes the long journey to your eyes. That is the strange and beautiful truth of looking at the night sky. Every glance is also a glimpse into the past, and Andromeda, modest, though it appears, offers one of the deepest glimpses available to the naked eye. And so, with that faint smudge now held in mind, let us ask, where did this light come from, and what has it seen along the way? Imagine, if you can, a single photon, a tiny packet of light born in the core of a star somewhere within Andromeda. 2.5 million years ago, this photon emerged from the surface of that star shot outward into space and began a journey that would outlast entire species. At the moment it left the Earth was home to creatures that looked something like us, but were not quite us. They walked upright. They used simple tools, but they had no language, no fire, no sense that one day their descendants would look up and catch the very light that was at that moment beginning its long voyage. The photon traveled at the speed of light, the fastest speed possible in the universe, 300,000 kilometers every second. It sounds almost instantaneous, and over human distances it is. Light from the sun takes only 8 minutes to reach us. Light from the moon takes just over a second. But the distance to Andromeda is so vast that even at this incredible speed, the photon's journey took millions of years. It flew through the void between galaxies, through regions where matter is so sparse that it might travel for thousands of years without encountering a single atom. As the photon raced through space, time passed on Earth. The ancestors who were alive when it began its journey lived, reproduced, and died. Their descendants did the same. Generation after generation, the slow work of evolution continued. Gradually, those early tool users learned to control fire. They developed language, art, culture. They spread across continents, adapting to forests, plains, mountains, and coasts. Ice ages came blanketing much of the planet in glaciers, and then receded, leaving behind a world reshaped. The photon flew on, oblivious, tireless, moving through the dark. It flew past the time when humans began to form the first permanent settlements, when agriculture replaced hunting and gathering, when the first cities rose from the plains of Mesopotamia. It flew past the construction of the pyramids, past the flowering of Greek philosophy, past the rise and fall of empires. It flew past the Middle Ages, past the Renaissance, past the Industrial Revolution. It flew through all of human history unseen and unseeing, carrying with it a message encoded in its wavelength, a fragment of information about the star that emitted it and the galaxy it came from. And then tonight, or perhaps last night, or perhaps tomorrow night, when you look up, that photon completes its journey. It crosses the threshold of Earth's atmosphere, passes through the air, and enters your eye. It strikes the retina, where it is absorbed by a cell, converted into an electrical signal, and sent to your brain. In that moment, you become the endpoint of a story that began before your species existed. The photon's journey, 2.5 million years in the making, ends with you. This is not a metaphor. It is the literal truth of seeing. Every time you look at Andromeda, you are catching photons that have traveled across unimaginable distances and unimaginable spans of time. Each one is a messenger from the past carrying news of a galaxy as it was long, long ago. The Andromeda you see is not the Andromeda that exists at this moment. It is a memory, a snapshot, a fossil frozen in light. By the time that light reaches you, the galaxy has moved on. Stars that shone then may have since died. New stars may have been born. The spiral arms may have shifted. The galaxy continues its life. But what you see is always the past. This quality of light, this built-in delay, turns the night sky into a kind of natural time machine. The farther away an object is, the farther back in time you see it. The stars you see with your naked eye are mostly within a few hundred light years, so you see them as they were a few hundred years ago. Andromeda, at 2.5 million light years, is much deeper in the past, and the most distant galaxies, visible through telescopes, are seen as they were billions of years ago, not long after the universe itself began. But Andromeda is special because it is close enough to see without any instruments at all. That faint smudge is accessible. It is there for anyone who looks, and every photon that reaches you from it is a direct personal connection to a moment in deep time. No one else will catch the exact same photons you do. They are yours alone, the endpoint of journeys that began when the world was young. To see Andromeda is to become part of its story, to receive a message sent before memory, before history, before everything we know as human. So now, knowing what that light has traveled through, let us turn to those who saw it before we did. The faint smudge we call Andromeda has been visible to human eyes for as long as humans have had eyes to see with. But knowing it was there and understanding what it was are two very different things. For most of human history, that pale blur remained a mystery, noticed by careful observers, but unexplained, catalogued, but not comprehended. The story of how we came to understand Andromeda is also the story of how we came to understand the universe itself. And it begins not with telescopes or mathematics, but with a simple act of noticing. In the year 964 in Persia, during what we now call the Middle Ages, an astronomer named Abd al-Rahman al-Sufi looked up at the night sky. He was compiling a book, a careful catalog of the stars and constellations visible from his location, updating and expanding upon the work of ancient Greek astronomers. As he traced the figure of Andromeda across the heavens, he noticed something unusual. Just off to the side of the constellation, there was a small patch of light that didn't behave like a star. It wasn't sharp. It didn't twinkle. it was soft, diffuse cloud-like. In his book, he described it as a little cloud, noting its position carefully so that others might find it. Al-Sufi did not know what this little cloud was. He had no way of knowing. The tools to measure its distance, to resolve its structure, to understand its nature did not yet exist. But he knew it was unusual, and so he recorded it. That simple act of documentation, of writing down what he saw, preserved the knowledge of Andromeda for future generations. His book was translated, copied past from scholar to scholar, across the Islamic world, and eventually into Europe. The little cloud became a fixture in astronomical texts, noted but unexplained, a curiosity awaiting interpretation. Of course, Al-Sufi was not the first to see it. Long before he looked up, others must have noticed that faint smudge. The ancient Greeks who named the constellation surely saw it on clear nights. Chinese astronomers, meticulous in their record-keeping, may have noted it as well. Indigenous peoples across the world who used the stars for navigation, for timekeeping, for storytelling, likely saw it and wove it into their own cosmologies. But if they did, those records have not survived in forms we can easily access. What remains is Al-Sufi's description, the first written account. We have a thread connecting us across more than 1,000 years to a man who looked at the same sky and wondered. For centuries, after Al-Sufi, Andromeda remained a mystery. It was called a nebula, from the Latin word for cloud, a term used for any fuzzy patch of light in the sky. Observers cataloged it alongside other nebulae, noting its position, its brightness, its shape, but no one knew what these nebulae were. Were they clouds of glowing gas within our own system of stars? Were they distant clusters, too faint to resolve individually? Were they something else entirely? The questions hung in the air unanswered as the centuries passed. Then in 1612, something changed. A German astronomer named Simon Marius turned a newly invented instrument toward the sky. The telescope, a simple arrangement of lenses in a tube, had only recently been developed, and Marius was among the first to use it for astronomical observation. When he pointed it at the nebula in Andromeda, the fuzzy patch became clearer, more distinct. It appeared as an elongated oval, still soft and cloud-like, but with more structure than the naked eye could perceive. Marius described it as resembling the flame of a candle seen through a thin sheet of horn. It was an evocative description, but it still didn't answer the fundamental question, what was it? For the next 300 years, astronomers continued to observe Andromeda and other nebulae, building better telescopes, making more detailed drawings, compiling more comprehensive catalogs. In the 18th century, Charles Messier, a French astronomer who hunted for comets, included Andromeda in his list of objects that might be mistaken for comets. It became Messier 31 or M31, the designation it still carries today. William Herschel, who discovered Uranus and built some of the largest telescopes of his time, studied it and speculated about its nature. But despite all this attention, despite all the improvements in observational technology, the fundamental question remained, was Andromeda part of our galaxy or something beyond it? By the early 20th century, the question had become urgent. Astronomers had discovered that some nebulae showed spiral structures, beautiful whirls of light that suggested rotation, motion, complexity. Were these spiral nebulae merely clouds of gas within the Milky Way, or were they separate galaxies in their own right? The debate reached its peak in April 1920 in an event now known as the Great Debate. At the Smithsonian Institution in Washington, two prominent astronomers, Harlow Shapley and Heber Curtis, presented opposing views. Shapley argued that the Milky Way was the entire universe, and that spiral nebulae, like Andromeda, were simply part of it. Curtis argued the opposite, that spiral nebulae were island universes, separate galaxies far beyond the boundaries of our own. The debate was inconclusive. Both sides made compelling arguments, but neither had definitive proof. The answer would require a measurement, a way to determine the actual distance to Andromeda, and that measurement came just 4 years later, in 1924, when a young astronomer named Edwin Hubble pointed the 100-inch Hooker telescope at Mount Wilson toward Andromeda and found something extraordinary. Hubble identified a type of star called a Cepheid variable within Andromeda. These stars are remarkable because they pulse in brightness with a regular rhythm, and that rhythm is directly related to their intrinsic luminosity. By measuring how long it takes a Cepheid to brighten and dim, an astronomer can determine how bright the star actually is. Then, by comparing that intrinsic brightness to how faint it appears from Earth, the distance can be calculated. It's a simple principle, elegant in its logic, and Hubble used it to measure the distance to Andromeda. The result was staggering. Andromeda was not within the Milky Way. It was far, far beyond it, more than 1 million light years away. The little cloud, the faint smudge, the nebula that had been noted for centuries, was not a cloud at all. It was an entire galaxy, a system of hundreds of billions of stars, comparable in size and structure to the Milky Way itself. And if Andromeda was a separate galaxy, then so were the other spiral nebulae. In a single stroke, Hubble's discovery expanded the known universe by an almost unimaginable factor. Before that night, the universe was thought to be the Milky Way and nothing more. After that night, it became clear that the Milky Way was just one galaxy among countless others scattered across an expanse so vast that light itself takes millions or billions of years to cross it. The universe didn't just grow, it exploded in scale, revealing a cosmos far grander and more mysterious than anyone had imagined. And Andromeda, the modest smudge that had been visible to the naked eye all along, was suddenly understood to be our nearest galactic neighbor, a sibling in the cosmic family. This shift in understanding is one of the most profound in human history. It changed not only how we see the night sky, but how we see ourselves. We are not at the center of everything. Our galaxy is not unique. We are part of a universe filled with galaxies, each one a city of stars, each one potentially home to countless worlds. And all of it began with people like Al-Sufi, who looked up and wrote down what they saw, and people like Hubble, who looked deeper and found the tools to measure what had seemed immeasurable. When you look at Andromeda now, you are part of that lineage. You are seeing what Al-Sufi saw, what Marius saw, what Hubble saw. The light is the same, the smudge is the same, but your understanding, built on the work of generations, allows you to see it not just as a cloud, but as a galaxy, a neighbor, a reminder that the universe is far larger and more wondrous than it appears at first glance. And now, with all this history held in mind, let me ask you something personal. Have you ever seen it yourself? Not in a photograph, not on a screen, not in a textbook or a documentary, but with your own eyes standing beneath the actual sky, looking up at the real thing. It's a question worth pausing over because the experience of seeing Andromeda directly is different from knowing about it in the abstract. Knowledge is one thing, presence is another. And while we can talk about light years and trillions of stars and ancient photons, none of that quite captures what it feels like to stand outside on a clear night and find that faint smudge for yourself. If you haven't seen it yet, that's all right. Many people haven't. The sky above most of us is washed out by the glow of electric lights, the brightness of cities that never sleep. Even if Andromeda is there shining as it always has, it can be hidden by the veil of light pollution. But the galaxy hasn't gone anywhere. It's still there every night waiting. And if you ever find yourself in a place where the sky is dark enough, where the stars spill out in numbers you're not used to seeing, then Andromeda becomes accessible. It becomes something you can meet. There's something important about seeing it with your own eyes, something that photographs can't quite replicate. Photographs of Andromeda are beautiful. They reveal a structure invisible to the naked eye, the spiral arms traced in blue and gold, the dark lanes of dust, the glow of star-forming regions, the subtle wisps of the outer halo. Telescopes can capture detail that makes the galaxy come alive in ways we could never see directly. But those images are mediated. They are processed, enhanced, displayed on screens. There's a layer of technology between you and the galaxy. When you see Andromeda with your own eyes, there is no mediation. The photons that left that galaxy 2.5 million years ago travel across space, pass through Earth's atmosphere, and enter your eye directly. There's no camera, no computer, no screen. Just you, the sky, and the light. It's a pure connection, unfiltered and immediate. And even though what you see is faint, even though it's just a smudge, the knowledge of what you're looking at transforms the experience. You're not just seeing light, you're seeing a galaxy. You're seeing the combined glow of 1 trillion suns caught in a single glance. People who have had this experience often describe it in similar ways. They talk about feeling small, but not in a way that's frightening or diminishing. It's more like a sense of relief, as if the daily concerns that usually weigh on them have suddenly become lighter. When you're standing beneath a sky full of stars, looking at a galaxy millions of light years away, the problems that seemed so large earlier in the day tend to shrink, not because they don't matter, but because they're placed in context. The universe is vast, ancient, indifferent to human worries. And somehow that vastness is comforting. It reminds you that you're part of something much larger than your immediate circumstances. Others describe a feeling of connection. Even though Andromeda is far away, even though it's incomprehensibly large, seeing it makes them feel less alone. We are made of the same materials as the stars. The atoms in our bodies were forged in stellar cores and scattered by supernova explosions. The carbon, oxygen, nitrogen, and iron that make up our cells once existed in stars that lived and died long before the sun was born. In that sense, we are literally made of stardust. And when you look at Andromeda, you're looking at a place where that same process is still happening, where stars are being born from clouds of gas and dust, where the elements of life are being forged in nuclear fires. You're connected, not just metaphorically, but physically, atomically, to the galaxy you're seeing. If you want to see Andromeda for yourself, there are a few things that help. First, you need darkness. Not complete darkness, but enough to let your eyes adapt, and for the fainter lights to become visible. City parks at night usually aren't dark enough. You need to get away from streetlights, away from the orange glow that hangs over urban areas. If you can find a place in the countryside, or by a lake, or on a mountain where the air is clear and the horizon is free of light pollution. Second, you need patience. Your eyes take time to adjust to the dark, usually about 15 to 20 minutes. At first, you might not see much beyond the brightest stars, but if you stay outside, if you let your eyes adapt, the sky will gradually reveal more of itself. Fainter stars will appear. The Milky Way, if you're far enough from city lights, will begin to show itself as a hazy band across the sky, and somewhere in that darkness, Andromeda will emerge. Third, you need to know where to look. Start with Pegasus, that great square in the autumn sky. From there, follow the line of stars eastward to Andromeda's constellation. Once you are in the right area, use averted vision. Look slightly to the side of where you think the galaxy should be. Let your peripheral vision, which is more sensitive to faint light, do the work. And if you're lucky, if the night is clear and dark, you'll see it. A soft oval, a gentle smudge. Easy to miss if you don't know it's there, but unmistakable once you find it. When you do see it, take a moment to just look. Don't rush. To check a star chart or take a photo or move on to the next object, just stand there and look at it. Let the knowledge settle in. That faint glow is a galaxy. It contains nearly 1 trillion stars. It's more than twice the size of the Milky Way. It's moving toward us slowly but inexorably on a course that will lead to a collision billions of years from now. And the light you're seeing left that galaxy when your ancestors were still learning to shape stone into tools. This is why seeing Andromeda matters. It's not just about checking it off a list or saying you've done it. It's about the experience of standing in the presence of something so much larger than yourself and feeling for a moment the scale of the universe. It's about recognizing that you're not separate from all of this. You're part of it. The atoms in your body, the ground beneath your feet, the air you breathe, all of it comes from the same cosmic processes that formed Andromeda. You are in a very real sense the universe looking at itself. So the next time you have the chance, if you find yourself under a dark sky, take a few minutes to look for Andromeda. Bring your patience, bring your curiosity, and bring the knowledge that what you're looking for has been there all along, quietly shining, waiting for someone to notice. When you find it, you'll join a lineage that stretches back through Hubble, through Marius, through Al-Sufi, through countless unnamed observers who looked up and wondered. You'll be doing what humans have always done, looking at the sky and trying to understand our place within it. And perhaps in that moment, standing beneath the stars, with that faint smudge visible in the corner of your vision, you'll understand why people have been looking up for thousands of years. The answers we've found have changed. Our tools have improved. Our knowledge has deepened. But the sense of wonder, the feeling of standing small beneath something vast that has never changed, Andromeda is still there, as it was for Al-Sufi, as it was for Hubble, as it will be for whoever looks up long after we're gone. And tonight, if you wish, it can be there for you too. Now, having met Andromeda, both through history and through your own potential encounter, let us begin to understand what this galaxy truly is. When you see that faint smudge in the night sky, what you're actually seeing is only a fraction of what's really there. Your eyes, remarkable as they are, can only gather the brightest light, the most concentrated glow. The smudge you perceive is the core of Andromeda, the dense central bulge where stars are packed closely together, where the combined light is strong enough to cross 2.5 million light years and still register on your retina. But the galaxy itself extends far beyond what you can see. The spiral arms, the outer regions, the halo of stars and dark matter that surrounds it, all these remain invisible to the naked eye, hidden not by distance alone, but by the simple limitation of human vision. The true scale of Andromeda is difficult to hold in mind. The galaxy stretches across approximately 220,000 light years from edge to edge. Think about what that means for a moment. A light year is the distance light travels in 1 year, moving at 300,000 kilometers every second, without pause, without slowing. 1 light year is already almost 10 trillion kilometers, a number so large it loses meaning in everyday terms. And Andromeda spans 220,000 of those years. If a photon were to leave one edge of the galaxy and fly across to the other edge, it would take 220,000 years to complete the journey, traveling all the while at the fastest speed the universe allows. To put it another way, if you could somehow travel at the speed of light, leaving Earth right now and heading toward Andromeda, you would arrive in 2.5 million years. And when you got there, if you wanted to cross from one side of the galaxy to the other, it would take you another 220,000 years. These are not timescales that human minds are built to comprehend. We think in days and years, perhaps in decades or centuries, if we're contemplating history. But millions of years, hundreds of thousands of years, these numbers slide past us without sticking too large to feel real. So let's try to bring the scale down to something more tangible. Our solar system, the sun and all the planets that orbit it, along with the asteroids, comets, and everything else bound by the sun's gravity, spans roughly 2 light years across if you count the outermost regions of the Oort cloud, that distant shell of icy bodies at the edge of the sun's influence. 2 light years. Andromeda, by comparison, is 110,000 times wider than that. You could line up more than 100,000 solar systems side by side, stretching them across space, and still not span the full width of Andromeda. Or try this. Imagine the sun as a grain of sand, a single tiny speck. At that scale, the nearest star, Proxima Centauri, would be another grain of sand about 4 kilometers away. The Milky Way would be a disk of sand grains scattered across a region the size of a continent. And Andromeda, at that same scale, Andromeda would be another continent of sand equally vast, equally scattered with grains. The comparison breaks down quickly because the numbers are so extreme, but it gives some sense of the immensity involved. And then there are the stars. Andromeda contains nearly 1 trillion of them. A trillion is 1,000 billion. If you started counting right now, 1 star per second, never stopping to eat or sleep or rest, it would take you more than 30,000 years to count them all. By the time you finished, assuming you somehow could, new stars would have been born, and old stars would have died, and your count would already be out of date. The galaxy is not static. It's alive with motion, with change, with a constant cycle of stellar birth and death. Each of those trillion stars is a sun in its own right. Many of them are larger than our sun, many smaller, but all of them shine with their own light, fusing hydrogen into helium in their cores, releasing energy that has traveled across space for millions of years to reach us. And many of those stars have planets, Some of those planets have moons. Each system is a world unto itself, with its own dynamics, its own history, its own potential for complexity. The sheer number of possible worlds within Andromeda is staggering. Even if only a tiny fraction of planets are capable of supporting life, the absolute numbers involved are enormous. But here's the strange thing. We can say these numbers. We can write them down. 1 trillion stars, 220,000 light years, 2.5 million years. The words come easily enough. But can we actually feel them? Can we hold them in our minds in any meaningful way? The honest answer is no. The human brain is not equipped to grasp quantities this large. We evolved to understand the world at human scale. The distance we can walk in a day, the number of people in a tribe, the passage of seasons. When we try to stretch our thinking beyond that, we run into limits. 1,000 we can sort of imagine, 10,000 maybe. 1,000,000 starts to become abstract. 1 billion is almost incomprehensible. 1 trillion, it's just a word. This is why numbers alone are never quite enough when we talk about galaxies. They give us precision, they allow us to compare and measure, but they don't convey meaning. To understand something as vast as Andromeda, we need more than mathematics. We need metaphor. We need poetry. We need to engage not just the analytical part of our minds, but the part that responds to stories, to images, to emotions. We need to find ways to bridge the gap between the scales we can feel and the scales we can only describe. And perhaps that's where you come in. You standing beneath the night sky, looking at that faint smudge. You are roughly 1.7 meters tall, give or take. You live for perhaps 80 or 90 years if you're fortunate. You occupy a space not much larger than your own body. By any cosmic measure, you are impossibly small, almost negligibly brief. And yet you have something that Andromeda, for all its size and all its stars, does not have. You have awareness. You have the ability to look outward, to ask questions, to wonder. You can see Andromeda and know what you're seeing. You can measure it, study it, tell stories about it. You can feel awe in its presence. This is the bridge between human scale and galactic scale. Not size, but consciousness. Not duration, but understanding. You are small, yes, but you are not powerless. Your mind can reach across millions of light years. Your thoughts can encompass trillions of stars. You can hold the image of a galaxy in your mind, even if you can't hold its full reality. And in that act of reaching, of trying to understand, you become something more than your physical dimensions suggest. You become a point of awareness in a universe that is mostly unaware, a consciousness capable of contemplating its own context. There's a paradox in this. The more we learn about the scale of the universe, the smaller we seem to become. And yet the act of learning, of understanding, makes us larger in a different sense. We are not diminished by the vastness of Andromeda. We are connected to it. The atoms in your body were formed in stars. The calcium in your bones, the iron in your blood, the carbon in your cells, all of it was forged in stellar furnaces, ejected by supernova explosions, and gathered into new generations of stars and planets. You are made of the same material as Andromeda. The difference is only in arrangement, in scale, in complexity. So when you look at that faint smudge, you're not looking at something entirely separate from yourself. You're looking at a part of the same story, the same cosmic history that produced you. The galaxy is immense, yes, almost incomprehensibly so. but you're part of the same universe. The light that travels from Andromeda to your eye is made of photons, tiny packets of energy, and your eye is made of atoms that once existed in stars like those in Andromeda. The boundary between you and the galaxy is less solid than it appears. You are both expressions of the same physical laws, the same fundamental forces, the same ancient processes that have been unfolding for billions of years. This is what it means to place yourself against the vastness, not to measure yourself and find yourself wanting, but to recognize the connection, not to feel erased by the scale, but to feel situated within it. You are small, and the galaxy is large, but you are both here, both real, both part of the same unfolding story. And your ability to see it, to think about it, to feel wonder in its presence, that ability is itself a kind of bridge away of spanning the distance between the human and the cosmic. And so, as we move forward, let us carry this with us, the knowledge that we are small but connected, brief but aware, limited but capable of reaching beyond our limits. The galaxy is vast, but it is not beyond our understanding. And part of that understanding is recognizing that Andromeda, like all things in the universe, does not exist in isolation. When we picture Andromeda, we often imagine it alone, a solitary spiral floating in the darkness of space, isolated and independent. But galaxies, like people, do not exist in isolation. They gather in communities, bound together by gravity, moving in relation to one another, across timescales that dwarf human history. Andromeda is not a lone traveler. It is the center of a family, the dominant member of a collection of galaxies that astronomers call the local group. And understanding Andromeda means understanding its place within this cosmic neighborhood. The local group is, in the grand scheme of things, a relatively small gathering. It contains more than 50 galaxies, though the exact number depends on how you define the boundaries and how faint an object you're willing to count as a galaxy. Most of these are small, faint, barely noticeable, even with telescopes. They are dwarf galaxies containing only millions of stars, rather than billions or trillions scattered around the larger members, like smaller houses clustered near the estates of the wealthy. And at the heart of this neighborhood, dominating the gravitational landscape, are two great spiral galaxies, Andromeda and our own Milky Way. Think of it as a small town in the vastness of the universe. Most of the buildings are modest, unassuming, easily overlooked. But among them stand two grand structures, two mansions that draw the eye immediately. These are Andromeda and the Milky Way, the gravitational anchors of the local group, the masses around which everything else orbits. Between them, they contain the vast majority of the stars in the neighborhood. The rest of the local group's members are satellites, companions, smaller galaxies that circle one or the other of the two giants held in place by gravity. Some of these satellites are visible even to amateur astronomers. M32 and M110, for example, are two elliptical galaxies that orbit close to Andromeda. They appear in telescopes as faint fuzzy patches near the main galaxy, like loyal attendants standing watch. M32 is compact and dense, its stars packed tightly together, giving it a brightness unusual for its size. Some astronomers think it may have once been larger, stripped down by Andromeda's gravity over countless orbits, leaving behind only its concentrated core. M110 is more diffuse, softer trailing streams of stars that suggest it too has been shaped by tidal forces, pulled and stretched by the gravitational influence of its much larger neighbor. Beyond these, there are dozens of dwarf galaxies scattered throughout the local group. Many are so faint that they were only discovered in recent decades, revealed by careful surveys that could detect subtle overdensities of stars against the background. Some of these dwarfs are irregular in shape, looking more like loose swarms of stars than structured galaxies. Others are spheroidal, smooth, and featureless, little more than dim glows in the darkness. Each one contains perhaps a few million stars, sometimes fewer. Compared to Andromeda's trillion, they are tiny, almost negligible. But they are still galaxies, still collections of stars bound together by gravity, still part of the story. The relationship between Andromeda and its satellites is not static. Gravity is constantly at work, pulling, stretching, distorting. Some of the smaller galaxies are being tidally disrupted, their stars drawn out into long streams that wrap around Andromeda like ribbons. These streams are visible in deep images of the galaxy, delicate arcs, and shells of stars that trace the paths of ancient encounters. They are evidence that Andromeda has grown over time by consuming its companions, tearing them apart, and absorbing their stars into its own halo. This process is ongoing. Even now, some of Andromeda's satellites are being slowly digested, their structures stretched and dissolved into the larger galaxy. This behavior is not unique to Andromeda. Our own Milky Way does the same. Right now, the Milky Way is in the process of consuming the Sagittarius dwarf elliptical galaxy, a small companion that is being pulled into streams that wrap around our galaxy multiple times. But because Andromeda is larger, its gravitational influence is stronger, its reach longer. The number of satellites it has absorbed over billions of years may be greater, and the evidence of those ancient meals is written in the structure of its halo. The streams and shells of stars surrounding Andromeda are like fossils, the remnants of galaxies that no longer exist as independent entities. Studying these satellites is important because they help us understand the environment in which Andromeda exists, the number of dwarf galaxies, their distribution, their histories. All of these inform our models of how galaxies form and evolve. According to current cosmological theory, large galaxies like Andromeda should be surrounded by many smaller ones, each embedded in its own halo of dark matter. The fact that we observe this pattern, that Andromeda and the Milky Way each have dozens of known satellites, supports the theory, though there are ongoing debates about whether we see as many dwarf galaxies as the models predict. Each new discovery helps refine our understanding. The local group as a whole spans about 10 million light years, a vast distance by human standards, but modest compared to the larger clusters of galaxies found elsewhere in the universe. Within this volume, Andromeda and the Milky Way dominate. They sit on opposite sides of the group, separated by about 2.5 million light years, their mutual gravitational pull slowly drawing them together. The smaller galaxies scatter between and around them, some closer to Andromeda, some closer to the Milky Way, all bound together by gravity into a loosely organized community. And here's something remarkable. This community is not eternal. Andromeda and the Milky Way are moving toward each other at about 110 kilometers per second. That sounds fast, and in human terms it is. But across the gulf of space that separates them, it's a slow approach. It will take approximately 4 billion years for them to collide. When they do, the local group will be transformed. The two great spirals will merge, blending their stars and gas and dark matter into a single, larger galaxy. The satellites that currently orbit them will be scattered, some flung into the intergalactic void, others absorbed into the merger. The neighborhood as we know it will cease to exist, replaced by something new. But that collision is still far in the future. For now, the local group remains, as it is a small cluster of galaxies bound together in the immensity of space. And at its center, Andromeda presides, the largest, the most massive, the gravitational anchor around which so much else revolves. Its place in this family is not just a matter of size, but of influence of the way its gravity shapes the motions and fates of its neighbors. To understand Andromeda is to understand not just a galaxy in isolation, but a galaxy in context, a member of a community, a participant in a gravitational dance that has been unfolding for billions of years and will continue for billions more. When you look up at that faint smudge, you're not just seeing a single galaxy. You're seeing the center of a system, a hub around which dozens of smaller galaxies orbit. The light that reaches you comes primarily from Andromeda itself, but the influence of those smaller companions is there too, written into the streams and shells that surround it, visible only in the deepest observations. The family is real, even if most of it is invisible to your eyes. And knowing it's there, knowing that Andromeda is not alone, but surrounded by a community of smaller galaxies, adds another layer to its story, another dimension to its immensity. Now, having seen Andromeda in its neighborhood, let us turn closer to home and compare it to the galaxy we know best. We live inside a galaxy. This simple fact shapes everything about how we see the universe. When we look at the night sky, the band of light that stretches across it, the Milky Way, is not some distant object. It is our home seen from within. We are embedded in its disk, surrounded by its stars, and because of that, our view is inherently limited. We cannot step outside and see the Milky Way as a whole. We cannot observe its spiral structure directly. We can only infer it from the distribution of stars and gas, from the motions of objects within it, from comparisons with other galaxies we can see from the outside. This is why Andromeda is so valuable. It is close enough to observe in detail, yet far enough that we see it from the outside, tilted at an angle that reveals its structure. When we look at Andromeda, we are seeing what a spiral galaxy looks like when you're not trapped inside it. And because Andromeda is similar to the Milky Way, in many ways studying it helps us understand our own home. It is a mirror reflecting back to us the kind of galaxy we inhabit. The Milky Way contains approximately 400 billion stars. That's an estimate because counting stars in a galaxy is difficult, but the number is probably accurate to within a factor of 2. These stars are arranged in a disk about 100,000 to 120,000 light years across, with a central bulge and spiral arms that wind outward from the center. From our position within the disk, about 26,000 light years from the center, we see the Milky Way edge on, which is why it appears as a band of light across the sky rather than a spiral pattern. Andromeda, by comparison, is larger. Its diameter is roughly 220,000 light years, nearly twice that of the Milky Way. It contains close to 1 trillion stars, 2 to 3 times as many as our galaxy. In terms of sheer size and stellar population, Andromeda is the bigger sibling, the more massive of the two. But size is not the only measure of a galaxy's character. The Milky Way, though smaller, may be forming stars at a higher rate than Andromeda, making it more active in that sense. And when it comes to total mass, including the invisible dark matter that surrounds both galaxies, the difference may be smaller than it first appears. Some estimates suggest Andromeda is 30 to 50% more massive than the Milky Way, but the uncertainty is large enough that they could be more evenly matched than we think. Both galaxies are spirals, meaning they have a disc-like structure with arms that wind outward from a central bulge. But there are differences in the details. The Milky Way is a barred spiral, meaning it has a central bar-shaped structure made of stars with the spiral arms extending from the ends of the bar. Andromeda does not have a prominent bar, or at least not one as obvious as ours. Its spiral arms are broader, its central bulge more pronounced, giving it a slightly different character. These structural differences likely reflect different histories, different patterns of star formation, different encounters with smaller galaxies over billions of years. At the heart of both galaxies lies a supermassive black hole. In the Milky Way, that black hole is called Sagittarius A, and it has a mass of about 4 million times the mass of the Sun. It sits at the exact center of our galaxy, surrounded by a dense cluster of stars that orbit it at tremendous speeds. In Andromeda, the central black hole is far larger, estimated at around 100 million solar masses. This is a staggering difference, more than 20 times as massive as our own. Such a massive black hole exerts a stronger gravitational influence on the stars around it, shaping the structure of the central bulge in ways that differ from the Milky Way. Yet, despite its size, Andromeda's black hole is relatively quiet. It is not actively consuming large amounts of matter, not producing the intense radiation seen in some galaxies with active cores. It sits dormant, a gravitational anchor, its presence felt through the motions of nearby stars. Both galaxies are also surrounded by satellite galaxies. The Milky Way has the large and small Magellanic Clouds, two irregular dwarf galaxies visible to the naked eye from the southern hemisphere, along with dozens of smaller, fainter companions. Andromeda has M32 and M110, along with its own collection of faint dwarfs. These satellite systems tell us about how galaxies grow, how they interact with their environments, how they accumulate mass over time. By comparing the satellites of the Milky Way and Andromeda, astronomers learn about the processes that govern galactic evolution on the largest scales. And then there is dark matter. Both galaxies are embedded in vast halos of this invisible substance, which makes up the majority of their mass. We cannot see dark matter directly, cannot detect it with telescopes, but we can infer its presence from the way galaxies rotate. Stars in the outer regions of both the Milky Way and Andromeda move faster than they should if only the visible matter were present. The conclusion is that there must be additional mass unseen but gravitationally significant, holding the galaxies together. This dark matter extends far beyond the visible disks, forming enormous halos that may stretch across millions of light years, overlapping in the space between the two galaxies. The differences between the Milky Way and Andromeda are important, but so are the similarities. They are both spiral galaxies of comparable size and structure. They are both surrounded by smaller companions. They are both dominated by dark matter. They are both evolving, changing over time, forming new stars, losing old ones, interacting with their environments. And they are both part of the same story, the same gravitational dance that will eventually bring them together. This is why studying Andromeda matters so much. We cannot see the Milky Way from the outside, cannot observe its spiral structure, directly cannot measure its full extent. But Andromeda gives us a model, a template. By studying its structure, its composition, its history, we learn about what our own galaxy must be like. Andromeda is not just a neighbor, it is a reflection, a way of seeing ourselves from a perspective we can never achieve directly. Imagine living in a city all your life, walking its streets, knowing its neighborhoods, but never seeing it from above. You understand the city from within, from street level, but you cannot visualize its overall shape, its pattern, the way it fits together as a whole. Then one day, you visit a nearby city, one similar to your own, and you see it from a hilltop or an airplane. Suddenly, you understand what a city looks like from the outside, and that understanding helps you picture your own home in a new way. That is what Andromeda does for us. It shows us the shape of a spiral galaxy from the outside, and that knowledge helps us understand the Milky Way. The two galaxies are also partners in a deeper sense. They are not just neighbors or reflections of each other. They are gravitationally bound, their fates intertwined. The mutual pull between them has shaped their histories and will determine their futures. In about 4 billion years, they will collide their stars, mingling their gas clouds, colliding and triggering new waves of star formation, their black holes spiraling inward until they merge into a single, even larger black hole. The resulting galaxy will be neither the Milky Way nor Andromeda, but something new, an elliptical galaxy formed from the remnants of both spirals. Some have already given it a name, Milko-Meda. For now, they remain separate, each maintaining its identity, each visible to observers in the other. If there are beings on a planet circling a star in Andromeda, they might look up at their night sky and see a faint smudge that is the Milky Way, just as we see Andromeda. They might wonder about it, study it, tell stories about it, and in doing so, they would be looking at us at our home from across the same gulf of space that we look across to see them. So when you think about Andromeda, think also about the Milky Way. Think about how they compare, how they differ, how they mirror each other. Think about the fact that we live inside one and look out at the other, using what we see to understand what we cannot directly observe. And think about the future when the two will become one, when the boundary between them will dissolve, when what were once two separate stories will merge into a single shared history. Having compared these two great spirals, let us now ask, how did we learn to measure such things? How do we know what we know? You cannot stretch a measuring tape across the void. You cannot send a spacecraft and wait for it to report back. And yet, we know with remarkable precision that Andromeda lies 2.5 million light years away. How, when you look up at Andromeda, that faint smudge hanging in the darkness, the challenge becomes immediately apparent. You cannot stretch a measuring tape across the void. You cannot send a spacecraft and wait for it to report back, not when the journey would take millions of years, even at the speed of light. You cannot reach out and touch it, cannot walk around it to see its edges, cannot weigh it on a scale. The gulf between us and Andromeda is so vast that every familiar method of measurement fails, and yet the galaxy is there real and present, and the question of its distance, its size, its nature demands an answer. The only thing that crosses that gulf is light. Photons traveling at 300,000 kilometers per second make the journey that nothing else can make. They arrive in silence, falling upon Earth, like gentle rain, carrying with them information encoded in their wavelengths, their brightness, their patterns. Light is the messenger, the only messenger we have, and learning to read its messages has been one of the great achievements of human science. The challenge was not just building telescopes to gather more light, though that helped. The challenge was learning what questions to ask of the light once it arrived, learning how to extract distance from brightness, how to decode motion from color, how to infer mass from the movement of stars too faint to see individually. For centuries, the question of distance seemed unanswerable. The stars were simply too far away, their positions unchanging, no matter where Earth moved in its orbit. Without parallax, without the shift in position that reveals depth, there was no way to measure how far they were. Andromeda, that faint smudge, might have been a cloud of gas within our own galaxy or something far beyond. No one knew. No one could know. The light gave no obvious clue, and then came a breakthrough, quiet and elegant, that changed everything. Astronomers discovered a type of star that pulses in brightness with a regular rhythm. These stars, called Cepheid variables, brighten and dim over periods ranging from a few days to several months, their light rising and falling like the beating of a heart. For a long time, this pulsation was merely a curiosity, interesting but unexplained. But in the early 20th century, a pattern emerged. The period of a Cepheid's pulsation, the time it takes to complete one cycle, is directly related to its intrinsic luminosity. A Cepheid that pulses slowly is intrinsically brighter than one that pulses quickly. This relationship, once calibrated by observing Cepheids, whose distances were known through other methods, turned these stars into cosmic yardsticks. The logic is simple and beautiful. If you observe a Cepheid variable and measure its period, you can calculate how bright it actually is, its true luminosity. Then, by comparing that true brightness to how faint it appears from Earth, you can determine how far away it must be. The dimmer it looks, the farther it is. It is the same principle that governs how a candle flame appears fainter the farther you move from it. But unlike a candle, whose true brightness you might not know, a Cepheid announces its luminosity through the rhythm of its light. It tells you what it is, and from that, you can calculate where it is. This is what Edwin Hubble did in 1924. Using the 100-inch Hooker telescope at Mount Wilson, he turned his attention to Andromeda and began searching for individual stars within it. The galaxy was faint, its stars almost impossibly dim, but the telescope was powerful enough to resolve them. And among those stars, Hubble found Cepheids. He measured their periods, watching them pulse over weeks and months. He calculated their intrinsic brightnesses. He compared those to their apparent faintness as seen from Earth, and from that comparison, he determined the distance. The number was staggering. Andromeda was not within the Milky Way. It was far, far beyond it, separated by more than 1 million light years. The measurement was not perfect by modern standards, later refined to 2.5 million light years, but it was close enough to prove that Andromeda was a separate galaxy, an island universe in its own right, close enough to expand the known cosmos by an almost unimaginable factor. In a single stroke, Hubble's use of Cepheid variables transformed our understanding of the universe. The Milky Way was not everything. It was one among many, and Andromeda was our nearest galactic neighbor. Since then, astronomers have refined the technique and added others. Type Ia supernovae, the violent explosions that mark the deaths of certain kinds of stars, have become another standard candle. These explosions are remarkably consistent in their peak brightness, shining with a luminosity that is nearly the same, regardless of where they occur. When a type Ia supernova flares in a distant galaxy, astronomers can measure its brightness, compare it to the known luminosity of such events, and calculate the distance. In this way, supernovae have extended our reach far beyond the local group, allowing us to measure galaxies billions of light years away. For Andromeda, though Cepheids remain the primary method, their regular pulsations a reliable beacon across the gulf. But distance is not the only thing light reveals. It also carries information about motion. When an object moves toward or away from us, the wavelengths of the light it emits are compressed or stretched by the Doppler effect. This is the same phenomenon that makes a siren sound higher pitched as an ambulance approaches and lower pitched as it recedes. With light, the effect shifts colors. Light from an object moving away from us is red-shifted, its wavelengths stretched toward the red end of the spectrum. Light from an object moving toward us is blue-shifted, its wavelengths compressed toward the blue. Most galaxies in the universe show redshift. They are receding from us as space itself expands, carrying them along like leaves on a swelling river. The farther they are, the faster they recede, a pattern that reveals the expansion of the universe itself. But Andromeda is different. When astronomers measured the spectrum of its light, spreading it into its component colors, and examining the positions of absorption lines, they found something unexpected. The lines were shifted toward the blue. Andromeda is not receding, it is approaching. This blue shift is not large. It corresponds to a velocity of about 110 kilometers per second in our direction. That may not sound fast, but it is significant. It means that the local gravitational attraction between Andromeda and the Milky Way is stronger than the general expansion of space. The two galaxies are falling toward each other, drawn together by mutual gravity, and that approach will continue. In about 4 billion years, they will collide their stars, mingling their structures, merging. The blue shift is not just a measurement, it is a prophecy written in the spectrum of light. And then there is mass. How do we weigh a galaxy when we cannot place it on a scale, cannot measure its gravitational pull directly? We turn again to motion, to the way stars orbit within the galaxy. Stars in Andromeda move in vast circles around the galactic center, held in their orbits by the gravitational pull of all the matter the galaxy contains. The speed at which they orbit depends on how much mass is present. The more massive the galaxy, the faster the stars must move to maintain their paths. By measuring the velocities of stars and gas clouds in Andromeda, by tracking their motion through shifts in spectral lines, astronomers can infer the total mass. What they find is both expected and mysterious. The visible stars and gas, all the matter that emits or absorbs light, account for only a fraction of the mass needed to explain the observed motions. Stars in the outer regions of Andromeda are moving far too fast for the amount of visible matter. They should be flung outward, escaping the galaxy entirely, unless there is additional mass holding them in. That additional mass is dark matter, an invisible substance that does not emit, absorb, or reflect light, but does exert gravitational influence. It surrounds Andromeda in a vast halo extending far beyond the visible disk, outweighing the stars and gas by a factor of 5 or more. We cannot see it, we cannot touch it, but we can feel its presence through the way it shapes the galaxy's rotation, through the velocities of stars that betray the hidden mass beneath. So the mass we measure is not just the mass of stars, it is the mass of everything, visible and invisible, gathered together in one gravitational system. And that mass for Andromeda is estimated to be around 1.5 trillion times the mass of the Sun, perhaps more. The uncertainty is large because dark matter is difficult to measure, precisely its distribution, hard to map, but the overall picture is clear. Andromeda is massive, a heavyweight in the local group, its gravity shaping not only its own structure, but the motions of the smaller galaxies that orbit it. All of this measured from afar. All of this inferred from light. The photons that reach us from Andromeda carry within them the signatures of distance, of motion, of mass. They arrive as faint glimmers, barely noticeable, easily missed if you do not know where to look. But when we learn how to read them, when we learn to decode the information they carry, they reveal secrets about objects so distant that we will never touch them, never visit them, never see them, except as patterns of light against the darkness. The act of measurement is not just about numbers. It is about translation, about converting the language of light into the language of distance and time, of size and scale. It is about taking what seems unmeasurable and finding a way to measure it after all. And so, when you look at Andromeda, know that what you see is not just a smudge of light. It is a message decoded. It is a distance calculated. It is a motion tracked. It is a mass weighed through the patient work of generations. The faintness of its glow does not diminish what we know about it. If anything, it makes that knowledge more remarkable. From so little light, we have learned so much. Now, with distance and mass and motion understood, let us turn to shape, to the structure that gives Andromeda its character. When you see photographs of Andromeda taken through powerful telescopes, one of the first things that strikes you is its shape, not the roundness of a sphere, not the irregularity of a cloud, but something more ordered, more deliberate. Spiral arms sweep outward from a bright central core, arcing across space in elegant curves that seem almost too perfect to be natural, and yet they are natural, the result of gravity and motion and time, the signature of a galaxy caught in the act of rotating, of organizing itself into patterns that repeat across the universe. Spiral arms are not unique to Andromeda. They appear in galaxies throughout the cosmos, from the nearby to the impossibly distant. Our own Milky Way has them, though we cannot see them directly from our position within the disk. But what exactly are these arms? That question, simple as it sounds, took decades to answer. And the answer, when it came, revealed something subtle and strange about the way galaxies work. The spiral arms are not solid structures. They are not physical objects that rotate as a unit, like the blades of a fan turning through the air. If they were, they would wind up tightly over time, the arms wrapping around the center again and again until they disappeared into a featureless blur. Galaxies rotate, but different parts rotate at different speeds. Stars closer to the center move faster in their orbits than stars farther out. And if the arms were made of the same stars throughout their history, they would twist beyond recognition after just a few rotations. And yet the arms persist, visible in galaxies that are billions of years old, their structure intact, their elegance maintained. The solution to this puzzle is that the arms are not made of the same stars forever. They are density waves regions, where stars and gas are temporarily more concentrated. Think of it like traffic on a highway. Cars move through a traffic jam, entering from behind, slowing down as they pass through the congested area, then speeding up again as they exit on the other side. The jam itself, the region of higher density, remains in roughly the same place, even though the individual cars are constantly changing. The cars flow through, but the pattern persists. The spiral arms of Andromeda work the same way. Stars move through them, spending time in the denser regions before continuing on their orbits around the galactic center. The pattern of the arms remains, but the stars within them are always different, always moving, always flowing through like water through a channel. This wave-like nature of spiral arms explains why they are such active regions, why they glow so brightly in photographs. As gas clouds move into the denser environment of a spiral arm, they encounter the gravitational influence of all the stars and matter concentrated there. That gravitational pressure compresses the gas, squeezing it into tighter and tighter clouds. And when gas is compressed, it collapses. The denser regions within the clouds fall inward under their own gravity, heating up, igniting nuclear fusion, and becoming stars. The spiral arms are not just patterns of existing stars. They are nurseries regions where new stars are being born, where the raw material of the galaxy is transformed into light. The stars born in these regions are often massive, hot, and blue. They burn with tremendous energy, fusing hydrogen into helium at prodigious rates, shining with a brightness that can outshine entire regions of older, cooler stars. But their brilliance is brief. Massive stars live fast and die young, burning through their fuel in just a few million years before exploding as supernovae. By the time they die, they have moved out of the spiral arm where they were born, carried along by their orbital motion around the galaxy, and in the arm they left behind, new stars have formed to take their place, born from the same clouds of gas and dust, continuing the cycle. The arms are constantly renewed, a pattern of star formation that traces the density wave as it moves through the disk. In Andromeda, the spiral arms are broad and prominent, sweeping across the galaxy's face in graceful arcs that span hundreds of thousands of light years. They are traced not only by the blue light of young stars, but by the dark lanes of dust that thread between them. These dust lanes are not empty spaces, not voids where nothing exists. They are dense clouds of particles, tiny grains of carbon silicon, and other elements scattered into space by dying stars and supernovae. These grains absorb visible light, blocking it from reaching us, creating the appearance of darkness. But the darkness is not an absence. It is a presence, a concentration of the raw material needed to build new stars. In visible light, these dust lanes appear as shadows cutting across the bright arms, like streaks of charcoal on a canvas. But if you could see in infrared, which penetrates dust more easily than visible light, the lanes would glow warmly, revealing the hidden reservoirs of gas and dust that fuel the galaxy's ongoing star formation. Infrared telescopes like Spitzer and Herschel have mapped these regions in detail, showing structures invisible to optical instruments, rings and arcs of material that trace the history of Andromeda's interactions with smaller galaxies. The dust is not decoration. It is essential the seed from which future generations of stars will grow. The arms are also threaded with emission nebulae clouds of hydrogen gas that glow red and pink when illuminated by the ultraviolet light of nearby young stars. These nebulae are star-forming regions, the places where the process of collapse and ignition is happening right now, or rather was happening 2.5 million years ago when the light we see tonight left the galaxy. By the time that light reaches us, the stars may have already formed, the nebulae may have dispersed, but the image remains frozen in the photons that traveled across the gulf to arrive at our eyes. Each photograph of Andromeda is a kind of archaeological record, a snapshot of processes that unfolded long before human history began. What makes Andromeda's spiral structure even more interesting is that it is not perfectly symmetrical. One arm is broader than the other, thicker, more pronounced. There are knots and irregularities, places where the pattern seems disturbed, pulled slightly out of alignment. These asymmetries are not flaws or imperfections. They are clues, evidence that Andromeda has not been left alone to rotate peacefully through space. It has interacted with other galaxies, felt the gravitational tug of passing companions, absorbed smaller systems that wandered too close. Some of those interactions were minor small galaxies, grazing the edges of Andromeda's disk, stirring the gas, slightly triggering localized bursts of star formation. Others may have been more dramatic collisions or near collisions that sent waves of density rippling through the galaxy, compressing gas, distorting the arms, leaving scars that persist for hundreds of millions of years. Evidence of these past encounters is written into the structure of Andromeda itself. In addition to the spiral arms, there are rings, concentric features that circle the galaxy's core like ripples spreading outward on a pond. These rings are unusual, not seen in all spiral galaxies, and their presence suggests that something disrupted the disk in the past. Perhaps a smaller galaxy fell through it, punching a hole that sent shock waves spreading outward, compressing gas as they went, triggering rings of star formation that have since aged and faded, but left their structural signature behind. The rings are fossils, evidence of ancient violence, of encounters that reshaped the galaxy and left it different than it was before. If we could see Andromeda as it truly is, not limited by the sensitivity of our eyes or by the brightness of the sky around us, it would dominate our view. The spiral arms would stretch across an area more than 6 times the diameter of the full moon. They would be visible in all their complexity, the bright clusters of young stars scattered along them like jewels, the dark lanes of dust weaving between the glowing nebulae, marking regions of active birth. The structure would be unmistakable, a grand design laid out against the darkness, a pattern that speaks of order emerging from chaos of beauty, arising from the simple laws of gravity and motion. But our eyes gather only the brightest light, the concentrated glow of the core and the inner arms. The outer regions, the full extent of the spiral, fade into invisibility, hidden not by distance, but by faintness. Telescopes change this. With long exposures and sensitive detectors, they can gather light over minutes or hours, accumulating what the eye cannot hold, revealing what would otherwise remain unseen. The result is an image where Andromeda comes alive, where its spiral structure is revealed in exquisite detail, where the arms trace their arcs across the frame. where the dust lanes appear as sharp streaks, where the star-forming regions glow in blue and red, marking the sites of ongoing creation. Each photograph of Andromeda is a kind of time capsule, a record of what the galaxy looked like 2.5 million years ago. The spiral arms we see in those images are not the spiral arms that exist at this moment. They are a memory, a snapshot of a galaxy caught in mid-rotation, frozen by the speed of light into an image that took millions of years to reach us. The galaxy has continued to evolve since that moment. Stars have been born and died. The arms have shifted, the density waves have moved through the disk, the patterns have changed. But we will not see those changes until their light reaches us, until the new information arrives to update the image we carry in our minds. And still the spiral persists. It is one of the defining features of Andromeda, one of the things that makes it recognizable, that gives it character and presence. The shape is not random. It is the natural result of rotation, of the way matter organizes itself when it is bound together in a disk and spinning through space. Spirals appear in nature, again and again in water, draining from a sink in hurricanes, seen from space in the arrangement of seeds in a sunflower. They are a universal pattern, a signature of flow and rotation, and in Andromeda, that pattern is written on a scale so vast that it takes hundreds of thousands of light years to trace. To see the spiral is to see the galaxy as a living system, not a static collection of stars, but something dynamic, something that breathes through cycles of star formation and stellar death, something that responds to its environment, that carries the scars of past interactions and the promise of future change. The arms are not just beautiful, they are functional essential to the galaxy's ongoing life. They are the places where Andromeda renews itself, where gas and dust are compressed into new stars, where the cycle that has been running for billions of years continues. Without them, the galaxy would be quieter, less active, slowly aging as its existing stars burned out one by one. With them, it remains vibrant, alive with creation, a spiral of light and motion turning slowly through the dark. And now, having traced the shape of the spiral, having seen how Andromeda organizes itself through rotation and density waves, we might pause and ask what else lies hidden within, what fills the spaces between the stars, and what holds the galaxy together when so much of its mass remains unseen. When we picture a galaxy, we often think of stars, bright points of light, countless in number, scattered across space like glowing embers. And it is true that stars are what we see, what catches our eyes, what defines the visible shape of Andromeda. But stars are only part of the story. Between them, filling the spaces that might seem empty, is something else entirely. Gas and dust, magnetic fields, and radiation, dark matter, and invisible halos all woven together into a medium that is as essential to the galaxy's life as the stars themselves. To understand Andromeda fully, we must look not only at what shines, but at what remains hidden, at the components that do not announce themselves with light, but shape the galaxy nonetheless. Begin with the space between the stars. It is not empty, far from it. The galaxy is filled with gas, primarily hydrogen, the simplest and most abundant element in the universe. This gas exists in vast clouds, some cold and dense, others hot and diffuse, spread throughout the disk and extending into the halo beyond. In the densest regions within the spiral arms, the gas is compressed by the passage of density waves, squeezed into clouds that can collapse under their own gravity to form new stars. These are the nurseries we spoke of earlier, the places where the raw material of the galaxy is transformed into light and heat. But not all the gas becomes stars. Much of it remains dispersed, drifting through the galaxy, cycling between different states. Hot gas, heated by supernova explosions and the radiation from young stars, expands outward, rising above and below the plane of the disk in great fountains. As it rises, it cools eventually, falling back down to be recycled into new clouds, new stars, new generations. This is the breathing of the galaxy, a slow rhythm that unfolds over millions of years. Andromeda inhales gas from its surroundings, pulls it into the disk, compresses it into stars. Then it exhales as those stars age and die, returning enriched material back into the interstellar medium. The cycle continues, has continued for billions of years, and will continue as long as there is gas to fuel it. Threaded through this gas are particles of dust. These are not dust in the everyday sense, not the lint and debris that gathers in corners. They are tiny grains, smaller than the width of a human hair, made of carbon, silicon, and other heavy elements forged in the cores of stars and scattered into space by supernova explosions. These grains are essential. They absorb and scatter starlight, creating the dark lanes we see in images of Andromeda, the shadows that cut across the bright arms. But more than that, they provide surfaces on which molecules can form, places where hydrogen atoms can meet and combine, building the molecular clouds that are the direct precursors to star formation. Without dust, the process of making stars would be far less efficient. The galaxy would be dimmer, less active, slower to renew itself. Woven into all of this are magnetic fields, invisible lines of force that thread through the gas and dust, guiding the flow of charged particles, shaping the structure of clouds. These fields are weak by terrestrial standards, but over the vast scales of a galaxy, they become significant, influencing how gas moves, how it collapses, how jets of material are launched from dying stars. And there is radiation energy in the form of light and particles streaming from stars, from supernova remnants, from the central black hole, filling the galaxy with a glow that spans the entire electromagnetic spectrum, from radio waves to gamma rays. All of this, invisible to the naked eye, fills the space between the stars, making what seems empty into something rich and complex. And at the very center of Andromeda, hidden within the bright core, lies something even more extreme, a supermassive black hole, an object so dense that not even light can escape its gravitational pull. This black hole has a mass approximately 100 million times that of the Sun, dwarfing the black hole at the center of the Milky Way by more than 20 times. It sits at the exact center of the galaxy, surrounded by a dense cluster of stars that orbit it at tremendous speeds, their motions governed by the immense gravitational field. You cannot see the black hole directly. It emits no light, reflects no light, offers no visual clue to its presence, but its influence is undeniable. The stars closest to it move at velocities that would be impossible without such a massive object at the center. By tracking their orbits, measuring their speeds, astronomers can infer the mass of the black hole, even though they cannot see it. It is a gravitational anchor, a singularity around which everything else turns a point, where the laws of physics as we know them break down, and space itself is warped into shapes we can describe mathematically, but cannot fully visualize. The black hole is not actively feeding, right now not consuming large amounts of matter, not producing the intense radiation seen in some galaxies with active cores. It is relatively quiet, dormant, waiting, but it is there, and it shapes the structure of the central bulge, the motions of stars, the distribution of gas. And in the distant future, when Andromeda and the Milky Way collide, their central black holes will spiral toward each other, slowly at first, then faster until they merge into a single, even larger black hole, releasing gravitational waves that will ripple across the universe. But that is still billions of years away. For now, the black hole sits in silence, a dark heart at the center of a glowing galaxy. Beyond the visible stars, beyond the gas and dust, there is something even more mysterious. Dark matter, this substance, whatever it is, does not emit light. It does not absorb light. It does not interact with electromagnetic radiation in any way we can detect. And yet it is there, making up the vast majority of Andromeda's mass. By some estimates, dark matter accounts for 85% of the galaxy's total mass, outweighing all the stars, all the gas, all the dust, combined by a factor of 5 or more. We know it exists because of the way the galaxy rotates. Stars in the outer regions of Andromeda move faster than they should if only the visible matter were present. The rotation curve, a graph of orbital velocity versus distance from the center, remains flat far beyond where it should drop off. This can only be explained if there is additional mass unseen but gravitationally significant, holding the galaxy together. That mass is dark matter, and it extends far beyond the visible disk, forming an enormous halo that may stretch across millions of light years, overlapping with the halo of the Milky Way in the space between. What is dark matter? No one knows. It is one of the great unsolved mysteries of modern physics. It is not made of atoms as we understand them, not made of protons and neutrons and electrons. It does not clump into stars or planets. It does not shine. It simply exists, exerting gravitational pull, shaping the structure of galaxies, holding them together when they should fly apart. Without dark matter, galaxies, as we know them, could not exist. The stars would disperse. The spiral arms would unravel. The structure would collapse. Dark matter is the invisible scaffolding, the framework upon which the visible galaxy is built. Surrounding all of this, extending far beyond the bright disk and spiral arms, is the halo. Not the dark matter halo, though that is there too, but the stellar halo, a diffuse cloud of old faint stars that orbit the galaxy in long elliptical paths. These stars are not part of the disk. They do not follow the neat circular orbits of the spiral arms. Instead, they wander in more chaotic trajectories, some diving through the disk, others swinging far out into the intergalactic void before falling back again. Many of these stars are ancient, formed in the early universe, older than the disk itself, and many are the remnants of smaller galaxies that Andromeda has consumed over billions of years. When a small galaxy wanders too close to Andromeda, tidal forces begin to tear it apart. Its stars are pulled away, stretched into long streams that wrap around the larger galaxy like ribbons. These streams are visible in deep images, faint arcs, and shells of stars that trace the paths of ancient encounters. They are fossils, evidence of galaxies that no longer exist as independent entities. Their stars now part of Andromeda's halo, their identities lost. Some of these streams are still falling in, still being absorbed, evidence that the process of growth of consumption is ongoing. Andromeda is not finished. It is still eating. still gathering mass from its surroundings still evolving. The halo extends far beyond what we can easily see, fading gradually into the space between galaxies. There is no sharp edge, no clear boundary where Andromeda ends and the void begins. Instead, the galaxy fades its influence, diminishing with distance, but never quite reaching zero. At some point, perhaps a million light years from the center, the halo of Andromeda blends into the halo of the Milky Way, the two overlapping in the space between. In a sense, the two galaxies are already touching, already interacting, even though their disks remain separated by 2.5 million light years. When you put all of this together, when you account not just for the stars, but for the gas and dust, the black hole, the dark matter, the halo, you begin to see Andromeda not as a static object, but as a living system. It breathes, drawing in gas and exhaling enriched material. It eats, consuming smaller galaxies and incorporating their stars into its own structure. It evolves, changing over time, responding to its environment, shaped by interactions and mergers, and the slow work of gravity. The stars we see, bright as they are only the visible tip of something far larger and more complex. This is what makes galaxies so remarkable. They are not just collections of stars, not just pretty spirals to admire in photographs. They are ecosystems, systems in which matter cycles between different forms, where energy flows from the cores of stars out into space and back again, where structures emerge from the interplay of visible and invisible forces. Andromeda is alive in a way that transcends biology, alive in the sense that it is dynamic, active, constantly renewing itself through processes that have been running for billions of years. And all of this is hidden. The black hole cannot be seen. The dark matter cannot be detected except through its gravitational influence. Much of the gas is invisible in ordinary light. The halo is too faint to notice without long exposures and sensitive instruments. When you look at Andromeda with your own eyes, you see only a faint smudge, a tiny fraction of what is really there. But knowing what lies hidden, knowing that the smudge is surrounded by halos and filled with invisible matter that it breathes and eats and evolves, changes the way you see it. The faintness no longer seems modest. It seems like a veil, a thin covering over something immense and complex, something that reveals itself only to those who look deeper, who ask questions, who refuse to accept the surface as the whole story. So when you think of Andromeda, now think of it not just as a collection of stars, but as a system, a galaxy that is more than the sum of its visible parts. Think of the gas cycling through it, the dust forming in dying stars, the black hole anchoring the center, the dark matter holding it all together, the halo extending far beyond what you can see. Think of it as something alive, something that has been growing and changing for more than 10 billion years, something that will continue long after we are gone. That is what a galaxy is. That is what Andromeda is. And that faint smudge in the sky, modest though it appears, contains all of it. So now, having explored what Andromeda is having, measured its distance, and traced its structure, having seen the visible and the hidden components that make it whole, we might turn to a question of a different kind. Not what is Andromeda, but what does it mean? What does it tell us about time, about ourselves, about the nature of seeing itself? Every time you look at the night sky, you're looking into the past. This is not a metaphor or a poetic flourish. It is the literal truth of how light works. the inescapable consequence of the fact that light travels at a finite speed. When you see the moon, you are seeing it as it was 1.25 seconds ago, the time it takes light to cross the distance between the moon and Earth. When you see the sun, you are seeing it as it was 8 minutes ago. The light that warms your face left the sun's surface 8 minutes in the past, and if the sun were to suddenly vanish, we would not know it for 8 minutes, not until the last of the light that had already been traveling reached us. This delay grows with distance. The nearest star beyond the sun, Proxima Centauri, is about 4 light years away, so we see it as it was 4 years ago. The bright stars that form the familiar constellations are mostly tens or hundreds of light years distant, so we see them as they were decades or centuries in the past. Some may have already died, their light extinguished, but we will not know it until the final photons they emitted complete their journey and arrive here. The night sky is not a snapshot of the present. It is a tapestry woven from light that left its sources at different times, some recently, some long ago, all arriving together to create the illusion of a single moment. And Andromeda, that faint smudge you can see with your own eyes, is among the deepest glimpses into the past available without a telescope. The light reaching you tonight left that galaxy 2.5 million years ago. 2.5 million years. Think about what that means. When those photons began their journey, the Earth was in the midst of an ice age. Our earliest ancestors' creatures, we would barely recognize as human, were learning to shape stone into tools. There was no language as we know it, no fire, no art, no cities, no agriculture, no written history. The photons flew through space, crossing the gulf between galaxies, while on Earth, species evolved, climates shifted, continents drifted, ice sheets advanced and retreated, and eventually, after an unimaginable span of time, creatures arose who could look up and catch that ancient light. So when you see Andromeda, you are not seeing it as it is tonight. You are seeing it as it was frozen in a moment from deep prehistory. The galaxy has continued to live, to evolve, to change. Stars that were shining when that light left have since aged and died. New stars have been born in the spiral arms, igniting in clouds of gas compressed by density waves. The black hole at the center may have consumed matter, flaring briefly before settling back into quiescence. Smaller galaxies may have wandered too close and been torn apart, their stars added to Andromeda's halo. All of this has happened, is happening, will continue to happen, but we will not see it until the light carrying that information completes its journey. This creates a strange disconnect between what we see and what is. The Andromeda that exists at this moment, the galaxy as it is right now, in whatever sense now has meaning across such distances, is not the Andromeda we observe. It is hidden from us, separated not by space, alone, but by time. We are always looking backward. When we look outward, always seeing the past, never the present. The universe is a natural time machine, and the farther we look, the deeper into history we peer. But the story does not end with a single moment, a single snapshot from 2.5 million years ago. Every second, new photons arrive. Every night, the light falling from Andromeda brings fresh information, though all of it is still from the past, still delayed by the same 2.5 million years. The galaxy is constantly sending us messages, a steady stream of light that began its journey long ago and arrives continuously moment by moment, an unending river of ancient signals. If you look at Andromeda tonight, and then look again tomorrow night, the photons entering your eyes will be different. They left the galaxy at different times, though those times are separated by mere days within a span of millions of years. The flow is constant. The message is always arriving, always old, always new. There is something both humbling and intimate in this. Imagine for a moment that Andromeda were destroyed tonight. Perhaps its central black hole suddenly consumed it, or a passing galaxy tore it apart, or some other catastrophe we cannot predict erased it from existence. If that happened, we would not know for 2.5 million years. For all that time, the light that had already been traveling would continue to arrive, carrying the image of a galaxy that no longer existed. We would look up and see it, night after night, year after year, millennium after millennium, unaware that we were seeing a ghost, a memory, a letter from someone who had already died. The light would keep coming, faithful and patient, carrying a message from the past, even as the source of that message had vanished into the dark. This is the nature of cosmic distance. Everything we see is a memory. The universe presents itself to us not as it is, but as it was, and the farther we look, the older the memory becomes. The most distant galaxies, visible through telescopes, are seen as they were billions of years ago, not long after the universe itself began. By studying them, astronomers are looking back to a time when galaxies were younger, smaller, more chaotic, still in the process of assembling themselves from the primordial gas that filled the early cosmos. Andromeda is not that far, not that old, but it is still distant enough that we see it as it was long before human history began. And yet, despite this separation in time, despite the fact that we are looking at an image from the distant past, there is also a connection. The photons that reach you from Andromeda are real. They are here now, falling upon your retina, absorbed by the cells in your eye, converted into electrical signals that your brain interprets as light. Those photons traveled for 2.5 million years to reach you, and when they arrive, their journey ends with you, not with anyone else, not with humanity as a whole, with you personally, individually. The photons that enter your eye are yours alone. No one else will catch those exact same photons. They began their journey in a star, within Andromeda, traveled across the void, passed through Earth's atmosphere, and ended in your eye. You are the conclusion of their story, the final destination, the place where their long voyage terminates. This creates an intimacy that seems to contradict the vastness of the distance. Andromeda is incomprehensibly far, and yet its light touches you directly personally. It is a connection across millions of years and millions of light years, a thread that links you to a galaxy you will never visit, never see, except as patterns of ancient light. But that thread is real. The connection is tangible. When you look at Andromeda, you are not merely observing it from a distance. You are participating in its story, receiving its light, becoming the endpoint of journeys that began before your species existed. To see is to travel through time. Every glance at the night sky is also a glimpse into the past, and Andromeda offers one of the deepest glimpses available to the naked eye. The faint smudge you see is a message from prehistory, a snapshot of a galaxy as it was when the world was young, when the story of humanity was just beginning, when the future was unwritten and unknowable. And that message arrives fresh every night, every moment, carried by light that has been traveling longer than memory, longer than history, longer than anything we can easily hold in mind. So, when you look at Andromeda, know that you are looking backward through time. Know that the galaxy you see is not the galaxy that exists at this moment, but a memory, a fossil frozen in light. Know that new photons are arriving constantly, carrying new slices of that ancient past, and that each one you catch is yours alone, a personal connection across an abyss of space and time. And know that in this act of seeing you are doing something profound. You are witnessing the past directly, not through artifacts or records, but through the light itself, the original messenger, the only thing that crosses the gulf and brings the distant near. Now, with this understanding of time and light held close, let us turn to another question, one that follows naturally from the immensity we have explored. Where do we fit in all of this? What does it mean to be human in the presence of such scale? When you place yourself beside Andromeda, the comparison is almost absurd. The galaxy stretches across 220,000 light years. You stand at most, perhaps 1.7 meters tall. The galaxy has existed for more than 10 billion years. You will live, if you are fortunate, perhaps 80 or 90. The galaxy contains nearly 1 trillion stars, each one a sun, many of them larger and brighter than our own. You are a single organism made of cells, temporary and fragile. How do you even begin to compare? What does it mean to set human scale against galactic scale? To place your brief life beside something so vast and ancient that the numbers themselves resist comprehension? The instinctive response is to feel small, and you're small at least in physical terms. There is no denying it. Your body occupies a tiny volume of space. Your lifespan is a flicker compared to the age of galaxies. The concerns that fill your days, the worries that keep you awake at night, the joys and sorrows that define your experience, all of it unfolds on a stage so small that it would be invisible from even the nearest star, let alone from Andromeda. If you were to vanish tomorrow, the galaxy would not notice. The stars would continue to burn. The spiral arms would continue to turn. The universe would proceed exactly as it would have if you had never existed at all. This can feel overwhelming. Some people, when confronted with the scale of the cosmos, describe a sense of insignificance, as though the vastness diminishes them, as though their existence becomes meaningless in the face of such immensity. But there is another way to see it, one that is both truer and more sustaining. Smallness is not the same as meaninglessness. Size is not the measure of value. A flower is not less important than a mountain simply because it is smaller. A thought is not less real than a planet simply because it has no mass. The human scale and the galactic scale are different, yes, but they are not in competition. They are both real, both valid, both part of the same universe. Consider what you have that Andromeda does not: consciousness, awareness, the ability to look outward and ask questions. Andromeda is vast, but it does not know it is vast. It does not wonder about its own size. It does not measure itself against other galaxies. It simply is existing without awareness, without curiosity, without the capacity to reflect on its own existence. You, on the other hand, small as you are, can see Andromeda. You can measure it. You can understand it at least in part. You can feel awe in its presence. You can tell stories about it, wonder about it, imagine what it would be like to travel there to see it from within. to stand on a planet circling one of its trillion stars and look back toward the Milky Way. This capacity for awareness is extraordinary. It is not diminished by your size or your brevity. If anything, it becomes more remarkable when placed against the vastness. You are a point of consciousness in a universe that is mostly unconscious, a mind capable of comprehending, however imperfectly, the very scales that dwarf you. That is not insignificance. That is something profound, something unique as far as we know. Andromeda is immense, yes, but it is also unaware. You are small, but you are awake. And there is more. You are not separate from the galaxy, not fundamentally different from it. You are made of the same materials. The atoms in your body, the carbon and oxygen and nitrogen and iron that form your cells, were not created on Earth. They were forged in the cores of stars fused together under temperatures and pressures so extreme that nuclei merged, building heavier elements from lighter ones. Those stars eventually died, some quietly shedding their outer layers, others exploding as supernovae, scattering their enriched material into space. That material, seeded with the heavy elements necessary for planets and life, drifted through the galaxy, eventually collapsing into new clouds, new stars, new planetary systems. Our sun formed from such a cloud, and the Earth condensed from the debris left over, and from that debris, life arose, and from life, eventually you. So, the atoms in your body are stardust, literally. The calcium in your bones was forged in a star. The iron in your blood was created in a supernova explosion. The oxygen you breathe with every breath was fused in the core of a massive star and released when that star died. You are not just standing beneath the stars, looking up at them. You are made of them. You are the universe looking at itself, matter that has become complex enough to be aware, to think, to wonder. Andromeda, and you are not separate. You are both expressions of the same physical laws, the same processes, the same story that has been unfolding for billions of years. This connection is not metaphorical. It is physical, atomic, undeniable. The elements that make up your body exist in Andromeda as well. Stars there are fusing hydrogen into helium, helium into carbon, into oxygen, building the periodic table through nuclear fusion, just as stars in the Milky Way have done. When those stars die, they will scatter their elements, and those elements may one day become part of planets, perhaps even part of life, if conditions allow. The process is the same. The materials are the same. You and Andromeda are made of the same stuff, separated only by distance and arrangement, not by fundamental nature. Knowing this changes the way you see yourself in relation to the vastness. You're not standing outside the universe, looking in. You are part of it, woven into it at the most basic level. The vastness does not diminish you. It contextualizes you. It shows you where you fit, how you arose, what you are made of. You are small, yes, but you are also connected, linked by matter and history, and process to everything else that exists. The boundary between you and the cosmos is less solid than it seems. You are not separate. You are continuous, and yet your smallness remains real. Your lifespan is brief. Your body is fragile. The things that matter to you, the relationships you build, the work you do, the experiences you have, all of it unfolds on a human scale, not a galactic one. And that is not a flaw. That is the scale at which meaning exists for you. Andromeda may be vast, but it does not love, does not create, does not wonder. You do. Your life, short as it is filled with things that the galaxy, for all its size and age, cannot experience. Joy and sorrow, connection and solitude, creation and loss, all of these are human. All of these are real. All of these have value that is not measured in light years or billions of years. So perhaps the question is not how to compare yourself to Andromeda, but how to hold both scales in mind at once, the human and the cosmic, the brief and the eternal, the small and the vast. You are both. You are a temporary arrangement of matter, yes, but also a point of awareness capable of grasping the immensity of the universe. You are fragile and brief, yes, but also connected to processes that stretch across billions of years. You are small, yes, but also capable of seeing, of measuring, of understanding things far larger than yourself. This is the gift of perspective. To stand beneath the night sky and see Andromeda is to feel both your smallness and your significance at once. You are tiny compared to the galaxy, but you can see it. You are brief compared to its lifespan, but you can measure it. You are made of the same atoms, subject to the same laws, part of the same story. The vastness does not erase you, it locates you. It shows you where you stand not at the center of everything, but as part of everything. And in that realization, there is a kind of peace, a recognition that you are neither insignificant nor separate, but simply one expression among countless others of a universe that is vast and ancient, and still somehow able to become aware of itself through you. So, when you look at Andromeda, do not ask whether you matter in comparison to it. Ask instead what it means that you, small and brief as you are, can see it at all. Ask what it means that matter can become conscious, that atoms forged in stars can arrange themselves into eyes and minds capable of wonder. Ask what it means that the universe has produced in you a way to know itself. The galaxy is immense, but you are awake. And in the end, that may be the most remarkable thing of all. Now, with this understanding of our place held close, let us look to the future, to what will happen when our two galaxies finally meet. The future is already written, at least in broad strokes. Andromeda is approaching us at 110 kilometers per second, drawn by the mutual gravitational attraction between the two galaxies. This motion is not a choice, not something that can be stopped or redirected. It is the inevitable consequence of gravity, of mass pulling on mass across the void. The two galaxies are falling toward each other, and they will continue to fall until they collide. The timing is predictable. In approximately 4 billion years, give or take a few hundred million, Andromeda and the Milky Way will meet. This is not speculation. It is prophecy written in the mathematics of motion, in the blue shift of Andromeda's light, in the trajectories that can be calculated and modeled with precision. 4 billion years is an almost incomprehensible span of time. It is longer than the Earth has existed in its current form. It is longer than life has existed on this planet. It is so far in the future that trying to imagine what the world will be like then becomes an exercise in futility. But the collision will happen. The galaxies are patient, and gravity is patient, and the slow dance has already begun. The first encounter will not be a simple crash. Galaxies are not solid objects. They are mostly empty space, with stars separated by distances so vast that even when two galaxies pass through each other, the chance of individual stars colliding is almost zero. Instead, what happens is more subtle, more grand. The gravitational fields of the two galaxies interact, pulling and stretching, distorting shapes, sending stars onto new orbits. As Andromeda approaches, its gravity will begin to tug on the Milky Way, and the Milky Way's gravity will tug back. Long before the galaxies actually interpenetrate, their outer regions will begin to feel each other's influence. Tidal forces will become significant. These are the same forces that raise ocean tides on Earth caused by the differential pull of gravity across a body. In galaxies, tidal forces stretch structures, pulling them into long streamers called tidal tails. Stars will be drawn out of both galaxies, flung into arcing streams that trail behind like ribbons in the wind. These tails can extend for hundreds of thousands of light years, bridges of stars connecting the two galaxies as they pass. Some stars will be thrown out entirely ejected from the system, sent wandering into the intergalactic void as orphans no longer belonging to any galaxy. And then the galaxies will pass through each other. The disks will overlap stars, from one mingling with stars from the other, though direct collisions between stars will remain vanishingly rare. The space between stars is simply too large. But the gas clouds, those are a different story. When gas clouds from the two galaxies collide, they do interact, compressing each other, triggering shock waves that can ignite enormous bursts of star formation. The collision will light up with the blue glow of millions of newly born stars, massive and hot, burning brightly for a brief time before exploding as supernovae. The night sky for any observers who might exist then will be filled with light, with new clusters, with nebulae glowing in shades of red and blue, with a brilliance unlike anything we see in our current quieter era. For those observers, if they exist, the view will be transformative. Andromeda, currently a faint smudge, will grow larger over millions of years. At first, the change will be imperceptible, too slow to notice within a human lifetime. But over millennia, over hundreds of thousands of years, it will become undeniable. The smudge will expand, becoming more prominent, its spiral structure visible even to the naked eye. Eventually, it will rival the moon in apparent size, then surpass it, stretching across a significant portion of the sky. And as the collision approaches, it will dominate the heavens, no longer a distant neighbor, but a towering presence, its spiral arms arcing overhead, filling the night with structure and light. Imagine standing on Earth or on whatever world might exist then, and looking up to see not one band of the Milky Way, but two galaxies overlapping their arms, intertwining stars scattered across the sky in patterns never seen before. The familiar constellations would be unrecognizable, the sky rewritten by the merger. And as the galaxies passed through each other and then fell back together, the view would change again, the patterns shifting new streams and arcs appearing the heavens in constant transformation. The first pass will not be the last. After the galaxies pass through each other, they will not simply continue on their separate ways. Gravity will pull them back. They will swing around, slowed by their mutual attraction, and fall toward each other again. This time the pass will be closer, the interaction stronger, more stars will be flung out, more gas will collide, more star formation will ignite, and then they will pass again and again, each time coming closer, each time losing energy to gravitational interactions, until finally, after perhaps 1 billion years of this slow dance, they will merge completely. The result will not be two galaxies, but one. The spiral structures will be destroyed, the ordered disks disrupted into a more chaotic elliptical shape. The new galaxy, sometimes called Milkomeda or Milkdromeda, will be a giant elliptical, smooth and featureless compared to the spirals that formed it. but larger and more massive than either was alone. It will contain all the stars of both galaxies, more than 1 trillion in total, along with the combined gas and dark matter, the merged black holes at its center. It will be a new entity, neither the Milky Way nor Andromeda, but something born from both. And what of Earth? What of us? 4 billion years is so far in the future that predicting the fate of our planet becomes almost meaningless. The sun itself will be near the end of its life by then, swelling into a red giant, possibly engulfing the inner planets. Earth may no longer be habitable, its oceans boiled away, its atmosphere stripped. Humanity, if it still exists in any recognizable form, will likely have moved elsewhere to other stars, other systems, perhaps even other galaxies. But if there are observers, if there are beings of any kind still present in this system, they will witness something extraordinary: the slow transformation of the sky, the merging of two great spirals, the birth of a new galaxy. It will be a spectacle that unfolds over millions of years, visible across generations, a cosmic event witnessed by whatever minds exist to see it. For us now, the collision is only a prediction, a future we can model but never experience. But knowing it will happen changes how we see Andromeda. That faint smudge is not static. It is approaching. It is already in motion, already falling toward us, already part of a story that will end with the two galaxies becoming one. The light we see tonight is from a galaxy on a collision course. And though the collision is billions of years away, the trajectory is set, the future written in the motion we can measure right now. And so, we return after all this exploration to the question we began with: how big is Andromeda really? We have numbers now: 220,000 light years across, nearly 1 trillion stars, a mass of 1.5 trillion suns. These are precise measurements, the result of centuries of observation and calculation. But do they answer the question, does saying that Andromeda is this many light years wide, or contains that many stars, actually convey what we mean when we ask how big it is? The truth is that numbers, for all their precision, are not quite enough. They give us a way to compare, to measure, to place Andromeda in context with other galaxies, but they do not convey meaning in the way that experience does. You can say that Andromeda is 220,000 light years across, but can you feel what that means? Can you hold it in your mind, visualize it, grasp it in any visceral way? The honest answer is no. The human brain is not built to comprehend scales like that. We evolved to understand the world at human scale, distances we can walk, sizes we can see, numbers we can count on our fingers. When we stretch beyond that, into the millions and billions and trillions, the numbers become abstract symbols on a page that we can manipulate mathematically but cannot truly feel. This is why size at the scale of galaxies becomes as much about meaning as about measurement. It is not just about how many kilometers or light years, but about what that size represents, what it makes possible, what it tells us about the universe. Andromeda is big not because it exceeds some arbitrary threshold, but because its size allows it to contain 1 trillion stars, each one a possible sun, each one potentially surrounded by planets, each one a world unto itself. The size is significant, not in itself, but in what it holds. And size is relative. Andromeda is large, compared to us, yes, almost incomprehensibly so. But it is small compared to galaxy clusters, which contain hundreds or thousands of galaxies. It is tiny compared to superclusters, which span hundreds of millions of light years, and it is negligible compared to the observable universe, which stretches for tens of billions of light years in every direction. Big and small are not absolute. They depend on perspective, on what you're comparing to, on the frame of reference you choose. Andromeda is both enormous and modest, both a giant and a speck depending on how you look at it. There is also the question of boundaries. Where does Andromeda end? At the edge of its visible disk? At the outermost spiral arm? At the limit of its halo, where stars fade into the intergalactic medium? At the boundary of its dark matter halo, which may extend for millions of light years beyond the visible structure? Galaxies do not have sharp edges. They fade gradually, their influence diminishing with distance, but never quite reaching zero. The size we quote, 220,000 light years, is a convention, a measurement of the visible disk. But the true extent of the galaxy, the region where its gravity dominates, is far larger and far harder to define. Size becomes less a fixed property and more a question of what we choose to measure. And perhaps that is the deepest answer to the question. Size is not an inherent quality of the galaxy. It is a concept we impose a way of organizing our understanding. Andromeda does not know how big it is. It does not measure itself. It simply exists, a collection of stars and gas and dark matter bound together by gravity evolving over billions of years. We are the ones who assign it a size, who draw boundaries, who count stars and calculate distances. The size exists for us, not for the galaxy. So what does it mean to ask how big Andromeda is? It means we are trying to situate ourselves in relation to it, to understand our place in the cosmos, to grasp something of the scale on which the universe operates. The numbers help. They give us precision, a way to compare and measure. But the meaning comes from somewhere else, from the sense of wonder we feel when we realize what those numbers represent, from the way they stretch our imagination, from the recognition that we, small as we are, can reach across such distances with our minds, even if we cannot cross them with our bodies. In the end, the size of Andromeda is not about the galaxy itself. It is about us. It is about what happens when human consciousness confronts the vastness of the cosmos, when we look up and see something so large that it challenges our ability to comprehend, and yet we try anyway. We measure it, we name it, we tell stories about it. We find ways to make it meaningful, to connect it to our own experience, to place it in the context of our lives. The galaxy is vast, yes, but we are awake. And in that awakening, in that act of seeing and wondering, the size becomes more than a number. It becomes a doorway, an invitation to think beyond ourselves, to stretch our understanding, to recognize that we are part of something far larger and older and more complex than we can fully grasp. And that perhaps is the real answer. Andromeda is as big as the wonder it inspires. And so we return, after all this journeying, to where we began, to the night, to the quiet, to the faint smudge of light hanging in the darkness above you. We have traveled far together, you and I, across distances measured not in kilometers, but in millions of light years, across spans of time measured not in hours, but in billions of years. We began with a simple question: how big is Andromeda really? And that question led us through layers of understanding, each one revealing something new. We started with a blur, a modest patch of light barely visible, to the naked eye easy to miss if you did not know where to look. And from that blur, we unfolded a galaxy. We learned its structure, the spiral arms that sweep outward in elegant arcs, the central bulge glowing with the light of ancient stars, the dust lanes that thread between the arms like shadows cast across light. We learned its population, nearly 1 trillion stars, each one a sun in its own right, many surrounded by planets, many of those planets perhaps harboring moons, atmospheres, weather landscapes we can only imagine. We learned its size 220,000 light years, from edge to edge, a span so vast that light itself, traveling at the fastest speed in the universe, would take more than 200,000 years to cross from one side to the other. We learned how to measure it, how astronomers used Cepheid variables to determine its distance, how they tracked its motion through the blue shift. In its light, how they inferred its mass from the velocities of stars orbiting within it. We learned about the components that remain hidden, the gas and dust that fill the spaces between stars, the supermassive black hole at its center, the dark matter that surrounds it in an invisible halo outweighing everything we can see. We learned its place in the cosmos, the center of a family of smaller galaxies, the partner to our own Milky Way, bound together by gravity in a dance that will end billions of years from now, in a collision that will merge them into one. And we learned about time, about the fact that every time we look at Andromeda, we are looking into the past, seeing the galaxy not as it is tonight, but as it was 2.5 million years ago. We learned that the light reaching us is ancient, that the photons entering our eyes began their journey long before our species existed, carrying a message from prehistory. And we learned about ourselves, about what it means to be small in a universe so vast, about how we are made of the same materials as the stars, about how our consciousness allows us to reach across the immensity and grasp, however imperfectly, the scale of what surrounds us. These are the things we have learned. Andromeda is our nearest large galactic neighbor. It is roughly twice the size of the Milky Way, containing nearly 1 trillion stars, compared to our few hundred billion. It is approaching us at 110 kilometers per second, drawn by mutual gravity on a course that will lead to a collision in approximately 4 billion years. It is visible to the naked eye on clear dark nights, a faint smudge that reveals itself only to those who are patient enough to look. These are facts, measurements, pieces of knowledge built over centuries of observation and calculation. But more important than the facts are the meanings we have drawn from them. We learned that being small does not mean being insignificant, that a human life, brief and fragile as it is not diminished by the vastness of galaxies, but contextualized by it. We learned that we are not separate from the cosmos, but part of it, that the atoms in our bodies were forged in stars scattered by supernovae and gathered into planets and life. We learned that looking up at the night sky is also looking backward through time, that the universe presents itself to us as a tapestry of light from different eras, all arriving together to create the illusion of a single moment. And we learned that the universe, vast and ancient as it is not indifferent, or rather, it is indifferent in the sense that it does not care, does not notice, does not alter its course based on our presence, but it is also generous. It offers itself to be seen, to be measured, to be understood. It sends us light constantly, patiently, across unimaginable distances, And in that light, we find connection, a thread that links us to objects we will never touch, places we will never visit, times we will never experience, except through the ancient photons that carry their images to us. So the next time you find yourself outside on a clear night, away from the glow of city lights, take a moment to look for Andromeda. Find the constellation Pegasus, that great square hanging in the autumn sky. Trace the line of stars eastward to Andromeda's figure, and there, just off to the side, use your peripheral vision, let your eyes soften, and look for that faint smudge. It will not be dramatic. It will not announce itself. But if the night is dark enough, and you are patient enough, you will see it. And when you do remember what it is, not just a blur, not just a patch of light, but an entire galaxy, 1,000,000,000,000 stars gathered into spiral arms, surrounded by halos of dark matter filled with gas and dust and the raw materials of creation. Remember that the light you are seeing left that galaxy 2.5 million years ago, when your ancestors were learning to shape stone, when the Earth was in the grip of an ice age, when the story of humanity was just beginning. Remember that the photons entering your eyes have traveled farther and longer than anything else in your life, and that their journey ends with you, personally, individually. And remember that this galaxy, distant as it is approaching. It is falling toward us, drawn by gravity on a course that will bring it closer and closer, until billions of years from now, the two galaxies merge. The faint smudge you see tonight is not static. It is in motion, part of a story that is still unfolding, a story that will end with transformation, with the birth of a new galaxy from the remnants of two old ones. As you stand there looking up, let the scale of it settle over you. Let yourself feel small, yes, but also connected. Let the worries of the day fade, if only for a moment, against the backdrop of galaxies and billions of years. Your concerns are real. Your life is meaningful, but they exist within a context so much larger than the immediate moment. The universe is vast, and you are brief, but you are also awake, aware, capable of grasping something of the immensity, even if you cannot hold it all. And when you are ready, when you have looked your fill, when the cold or the late hour calls you back inside, carry that image with you. Carry the faint smudge, the knowledge of what it contains, the sense of connection across time and space. Let it be a companion as you settle into bed, as you close your eyes, as sleep begins to pull you under. The galaxy will still be there tomorrow night, and the night after, and the night after that. Its light will continue to fall patient and constant, waiting for the next person to look up and notice. There is a peace in this, in knowing that you are part of something so much larger than yourself. Your anxieties, real as they are, shrink slightly when placed against the scale of galaxies, not because they do not matter, but because they are situated, placed in context. You are small, yes, but you are also part of the universe, made of its materials, subject to its laws, capable of understanding it. And that is enough. That is more than enough. So, as sleep comes, let Andromeda be with you. Let the glow of 1,000,000,000,000 stars faint as it is accompany you into dreams. Let the knowledge that you are stardust, that you are connected, that you are both small and significant, settle into your mind like a gentle weight, comforting rather than crushing. The universe is vast, but it has produced you a point of awareness, capable of looking back at itself and feeling wonder. And in that wonder, there is meaning. In that connection, there is peace. Thank you for sharing this journey. Thank you for looking up with me, for asking questions, for being willing to stretch your imagination across distances and times that resist comprehension. Andromeda is still there, as it has been for billions of years, as it will be for billions more. Its light is still falling, still crossing the void, still arriving fresh every moment to anyone who chooses to look. And whenever you need it, whenever you feel lost or small or overwhelmed, you can look up. You can find that faint smudge. You can remember what it is, what it means, and how you are connected to it. Sleep well, dream deeply, and know that the universe, vast and ancient as it is, holds you within it, not as an accident or an afterthought, but as part of its ongoing story. You are here, you are awake, and that in the end is the most remarkable thing of all. Until we meet again, under another sky, in another story, in another journey, through the quiet mysteries of science and sleep. Good night.